Hello everyone, this is Faggot and today I'm going to show you how to differentiate by first principles. So, the basic premise of this is you're finding the instantaneous rate of change. So, you're doing this as we did last time. So, say you've got just a little parabola, and that'll be like f of x equals 2x, let's do equals, whoa, why is my razor so sketchy? Equals x squared plus 2x. So this parabola here, as we can see, to find the instantaneous rate of change at say point, I reckon that'd be, 2, 0, assuming that's where the intercept is, hopefully. Hopefully I haven't stuffed that up that badly. To figure out the instantaneous rate of change here, we need to find, we can use the secant. So again, between the point there and the point there, we can find the average rate of change over that line. And the basis of first principles is making the distance between those points so small that it eventually becomes zero. So the distance between the length of the secant approaches zero to get a more and more accurate estimate of the average rate of change, which, as we saw in the instantaneous rate of change, which, as if you saw in my previous video, is how you can get more and more accurate. You can just by getting closer and shorter. So yeah, anyway, to find the instantaneous rate of change, by first principles. So the basic equation is if you're going, so your general average rate of change, f of a minus f of b on a minus b. So when you're differentiating by first principles, you're pretty much you're using this, but with a h, so the height of the distance that you're changing. So if you're trying to find a gradient, m equals f of x plus h minus f of x on x plus h minus x. And these x's cancel, which just leaves you with f of x plus h minus f of x. F of x on h. So that's like your general formula you can use for everything. So if we were to use for this equation, so f of x plus h equals x plus h whole squared plus 2x plus h, which equals x squared plus 2xh plus h squared plus 2x plus 2h. And right, and then f of x obviously equals x squared plus 2x. Okay, so now that we know this, we can plug this into our equation and find the derivative. So f dash x is the symbol for the derivative, and this is like your general equation for your instantaneous gradient. So instantaneous rate of change. So we'll plug these numbers in. So x squared plus 2xh plus h squared plus 2x plus 2h minus f of x, which is x squared, so minus x squared, and then minus 2x, because obviously both minuses. Right, so, and it's all on h. So this can be simplified, so you get negative x squared cancels with your positive x squared, your negative 2x cancels with your positive 2x, which just leaves you with 2xh plus h squared plus 2h on h, which again simplifies because every term has a h in it, so h goes out of there, h squared gone, divided by h, and divided by h. So it just leaves you with, and also for each of these, your limit to h approaches 0, because otherwise you don't get method marks, because it's actually technically incorrect, because otherwise it's just a bunch of random numbers really. So limit h approaches 0, and then that's 2x plus h plus 2, and because h is approaching 0, f dash x, or your derivative, equals 2x plus 2, which is very simple. And now, if you wanted to find, say, the instantaneous rate of change at f of 3, so we know that's the rate of change will be 2 times 3 plus 2 equals 8. So that would be your instantaneous rate of change at point x equals 3, which, if you look on the little graph at the top here, do about right, I reckon. About 8. So yeah, that's how you find the derivative and differentiate by first principles. Now there are easier ways, and I'll show you in the next video how to do this more easily, but whenever they ask you to do it by first principles, this is how you go about it. Thanks for watching, this has been Vagatiu, and goodbye.